So starting from the previous lesson, so we covered this example 6.1 regarding the simple fixed point iteration method. Okay, so in this simple fixed point iteration method, we write the equation in the form, in this form. Yeah, gx is equal to x. That means we rearrange the equation in such a form that on one side of the equation, either on the left or right side, we have the term, only term remaining, which is x. And then uh, the other terms which are remaining on the other side of the equation are calculated iteratively. Yeah, so by using this formula, xi plus 1 is equal to g of xi. And then we see this with the help of the example. Example 6.1. For the case of e power minus x function of x. So in this case, since this minus x is on the is in the original equation, we take x on the other side, and we can write xi plus 1 is equal to e power x minus e power minus x to the I. That means the value of this e power minus x gives the value of x, but that value of x we can use for the next iteration. Okay. So we did this, okay, and then we also find the percentage true error, okay, percentage true error. And then we found that the percentage true error is reducing, okay. But that reduction in the percentage true error is in a linear manner. That means I think almost 0.5 to 0.6 times the value each time the percentage true error was reducing. So it means that in this case, the convergence to this to the solution is in a linear fashion. So it is not too bad, but it is also not too good compared with some other methods. Let's see one more example. Separate the equation e power minus x minus x is equal to 0 into two parts and determine its root graphically. So we can separate this equation into two parts. So one part is this term, the e power minus x. So we take it as y2, okay, is equal to e power minus x, and the other part is x. So we can take this as y1. So this equation then can be actually y2 minus y1. So we can plot this y2 and y1. We can plot these y2 and y1. And then we can see where their values are intersecting with each other. So the plot is shown here again in this figure. So this is the so this figure A shows the plot of e power minus x minus x. That means for the total function. But for the parts of this function, so this is the blue line is for the for y1 that is equal to x. Okay, y is equal to x, and for the other part, it is y2. It is e power minus x. So at both at a point where these two curves are intersecting is the solution. It is the approximate solution by the graphical method. So which is the same as where the function is intersecting the x-axis at at a value of f of x is equal to 0. So therefore, this is another way for representing this method. Okay, so you can see in the previous slide as well, we can calculate these two functions at various values of x, starting from 0 to 0 0.2, 0 0.4, 0 0.6, 0 0.8, and 1. And then for each of these values of x, we can calculate these functions y1 and y2. So we can see that as x increases, the y1 increases. As x increases, the y2 decreases from 1 to there. And there is some point over here between 0 0.4 and 0 0.6 where the value of the function y1 changes from 0 0.4 to 0 0.6, and where the value of the function y2 changes from 0 0.67 to 0 0.54. So somewhere there may be an there may be a common point at which both values of y1 and y2 will be equal, and that will be the solution. So this is some talk about the convergence by this method. However, when we further explore this method, we can say that we cannot get the convergence in all situations. Okay, so first see that in this case, these two first of these two cases are showing that the convergence can be obtained. So what is the method suggesting to us? So the method suggests by this method, the mechanism of the method is such as like this. So for example, the mechanism of this, what is this mechanism of this method? The due to the formulation of this method, so we have one side of the equation is equal to x. Okay, so this method, that is the simple fixed point iteration method, can be translated into a general methodology in which one of the curve will be always y is equal to x. Okay, so and the other curve can be any. Okay, that will be the g of x. Okay, so this means one of the curve will be y is equal to x. So for example, in case A and in case B, y1 is equal to x, so y is equal to x is one of the curve in this method. But the other curve can be any, because that will depend on the how the shape of gx will come out. Okay, so in this case, then when we apply the iterative approach, so we have to start from x0. Okay, and then from x0 we will go to x1, we will go to x2. And in this graphical representation, we can clearly see that the solution is at this black dotted point. Okay, but we are starting from x0. Okay, so from x0 we can calculate the value of y2. So by the formulation, this will be the same value as for y is equal to x. So therefore, from here we will move to this point. Okay, and then for this value of x, we can calculate the value of y of y2. So which will give this value of y2, and from this, since this value of y2 will be the same as for this value for the next iteration, and then we can see that by each iteration in this case we are moving closer to the solution. So in this case we can see that the solution is converging. The solution is converging. Similarly, it is the case for this case B. So we start from x0 So we move to y is equal to x, and then we move to y2 is equal to gx, and then when we move to y is equal to x, and then we move to y2 is equal to gx. So basically in this method we move from one curve to the other after one after the other. And by doing so, we are coming closer to the solution. That means the solution will be converging. So this is a graphical or a graphical way of representing the convergence in this method. Okay. Uh, in the other two cases over here, there can be situations like this. So in these two cases, C and D, there the solution is not converging and as we can see now, as before, one of the curve is y is equal to x, because this is according to the methodology of this section. So one side of the equation is always equal to x, but the other curve can be can be any. So in this case, this curve is something like this, and the other curve is something like this. But in this case, the solution will not converge. This is how you can see like this. So for example, if we start, and you can see that the correct solution is at this black dotted point. So we can see that how the x naught is moving. So x naught is going from here, and then we will move to here, and then it will go to there, and then it will move to here. So as the method or suggests that, so we have to move from one curve to the other. Okay, and then by doing so, we are seeing we can see that we are moving away from the solution. So in this case, the solution will not converge. So similarly, in this case, you can see that we are moving away from the solution, or we are not finding solution at all is equal in this case. So there is no convergence. So this means that there is a problem in this method. So solution can converge, but in some other formulation, the solution may not converge. Okay, so the convergence is the solution. So what can be the conclusion by this discussion? So fixed points iteration method converges if the slope of the function gx is less than 1. So how we can see that from here? So for example, in this case, you can see that y is equal to x has a slope of 1. Okay, from the elementary geometry, we know that this is the 45-degree line. Okay, and this has a slope of 1. And in this case, if you see that the other curve y2 is equal to gx in the solution range, you can see that the y2 is equal to gx is a flatter curve than the y is equal to x. So it is not steeper than y is equal to x. This means that the slope of y2 is equal to gx is less than this, the y is equal to x. So in another word, because the derivative, the derivative represents the derivative of that function represents the slope. So the slope of this g of x is less than 1. So we can see that the solution is converging. But in this case, when the solution was diverging, the y2 is equal to gx is actually a steeper function than the y is equal to x. And in this case, we can see that the solution is not converging. By each iteration, we are moving away and away from the solution. So therefore, you can see from here that the absolute value of the derivative of this function x should be less than or equal to 1, should be less than 1. Only then the solution will converge. So when the method converges, the error is roughly proportional to or less than the error of the previous step. So therefore, it is called as the linearly convergent. So it is linearly convergent. So you can see that the error is gradually reducing in this case, like this in this case. the error is gradually reducing. So from 100 to 76.1, so it is about 0.76 times. From 76.3 to 0.35, it is also about 0.76, 0.76.7 times. So the error is linearly reducing, okay? So that's why we can say that this is a linearly convergent method, okay? So, so these are the two conclusions which we can draw. Any questions?
No.
Hmm. Okay, thank you. No questions. Okay. So then that means it's clear. Okay, next is the, can you hear me clearly?
Yes.
Okay.
Yes.
Okay, next is the Newton-Raphson method. So we have completed our discussion about the simple fixed point method. So in the simple fixed point method, we have drawn two conclusions. So if the slope of the function which we are which we are using for the simple fixed point method is less than the slope of the other function, which is y is equal to x, then we can get the convergence. And that the convergence in the previous method is a linear convergence. That means linearly converges. However, in the Newton-Raphson method, the convergence is much faster. Okay. So in the Newton-Raphson method, it is the most widely used method. It is based on the Taylor series expansion. So, so as we know that from the our chapter number 2, lecture number 2, the Taylor series of expansion can be written like this: f of xi plus 1 is equal to f of xi plus f prime of xi into delta x. That is, delta x is the change in the value of the x, that is xi plus 1 minus xi. And then similarly, this series continues to the higher powers, and then higher orders delta x terms. Okay, so the root is of the value of xi plus 1 when f xi plus 1 is equal to 0. And if we rearrange the terms, I'm not going into the exact algebra of this method. So we will be focusing mainly on the final relation for this method. So suppose if we put fx plus I is equal to 0, then we have xx fx I, and then f prime of xi, and then delta x is written as fx plus I plus 1 minus f xi. So then we can solve for this xi plus 1, because this is the this will be our solution. So if we solve for xi plus 1 by doing some simple algebra, xi plus 1 will be the equal to xi minus f of xi over f prime of xi. So you can see that this is the formula which we can use for Newton-Raphson method. And to remember to visualize this formula into your mind, so you can see that this formula is very simple to the one, very similar to the one we already used in chapter number 2 for approximations. And however, but in this formula, what we can see that we can get the next iteration by finding the value of the function and then dividing by the value of the derivative of the function. So that will give, and then we will take the ratio and then we'll subtract it from that value of x, and then that will give us the iteration for the final for the next term. So function divided by the derivative of the function, and then this is the value of the x. So uh, uh, conceptually, it is very easy to understand the formula by this method, by this visualization. Okay, function divided by the derivative, and then You can see that this is the value of x over here. So it is actually a convenient method for functions whose derivatives can be evaluated analytically. It may not be convenient for functions whose derivatives cannot be evaluated analytically. So yeah, so this is as you can see that it requires finding the derivative of the function. So for example, if it is sine x, the derivative will be cosine x. It is the function is x cubed minus x squared. So the derivative will be 3x squared minus 2x. So like that. So for these kind of functions, we can find the derivatives easily. Graphically, it shows like this. Okay. So for example, if this is the function which is represented by this blue curve, and then if we take a point on this curve xi, starting from xi, and then at that point, if we draw a tangent to this point, if we draw a tangent to this point, then sorry. If I draw a okay, so if I draw a tangent to this at this point, so you can see that this tangent intersects this x-axis at xi plus 1. So this will be our next iteration. Okay, and then next in the next point, what will you do? So from this point, you will go to this point over here, and then we will draw another tangent over here, and then we can see that in this way we will be getting closer to the solution in a rather very quick way. Okay, so this is the Newton-Raphson method approach over here. Okay. Why do we draw the tangent? So if you see that the formula of this equation uses the derivative, and the derivative is the slope of the tangent to the function. Okay, so slope is equal to f prime of xi. Okay, so that's why this function, this methodology brings us closer to the solution very quickly. So let's see it with the help of the example. So let's apply this the same method by the for the function which we used for the previous simple fixed point method, e power minus x, implying an initial guess of x naught is equal to 0. So the first derivative of the function can be evaluated at f prime is equal to e power minus x minus 1. So for example, if it is the function is e power minus x. So if you will take its derivative, so it will be minus e power minus x, and for x it will be minus 1. And then we can see that we can now perform the calculations. So which can be substituted along with the original function into this previous equation, this one. Equation 6.6. In the equation 6.6, we have the function f of x over here, and then we have f prime of x in the denominator. And then iteratively, we can solve this equation starting with the initial guess of 0. So we can start with the initial guess of 0. So this iterative equation can be applied to complete this. So in this case, you can see that within 4 iterations, we get a true percentage error of less than 10 to the power minus 8. So let's see how it how we can do it. So let me show you in this example. Okay, so maybe I, okay, so I is representing the iterations. Okay, 0, 1, 2, 3, 4, 5. Okay, maybe five iterations are enough. And then the values of xi. Okay, that means our first. So that means firstly we assume that it will be 0. Okay. Firstly, we assume that it will be 0. And the next is that because now the function is xi minus fx over f prime of x. So, and the function was like this. Okay, the function is this. The function is e power minus x. Okay, so this was the function. Sorry. Minus x. So this was the function, and then the derivative was derivative is equal to minus, sorry, the derivative is minus e power minus x, okay, minus 1. So this was the derivative, okay, and okay, so the derivative is this, okay. So we have to evaluate over here, and in the formulation it is like the formula is the formula for the Newton-Raphson method is, the formula is x minus f of x divided by f prime of x. This is the formula. Okay, so we will iteratively apply this formula. So the formula is x. So value of x is this one. The value of the function is, so minus value of the function. So function is this e power minus x minus 1. So it is e. So for e, I will put exponent, okay, function of the xl minus x. X is this value, okay, and minus x. X is also again this value, okay, and then I need to close this bracket and then divided by the derivative. So derivative will be also derivative is minus e power minus x. Okay, so it is minus exponent minus x. So minus x is this, and then minus 1. Okay, it is minus 1. So if I hope it is, if I entered the values correctly, so I get now 0.5. And then once I have now selected, established this formulas, and then I can just drag it down and then to calculate the values of 1. So I can see that by using this approach, the function has very quickly converged to the true solution. Okay, to converge to the true solution. Maybe I can show some more number of digits. Oh, sorry. Yeah, more number of digits here. Yeah, it's quite even more. Yeah. So very closely it is moving to the true solution. So what is the true error? Okay, so the true error maybe ET. So the true error can be found as, because the true solution was I think something like 0.5714. Okay, so for example, I already calculated before in the last lecture by the solver operation. So true solution was this. So the true x is equal to here, this value. So let's see, the true value is true value is this. Copy and yeah. So this is the true value. Okay. Maybe take some more. Yeah, this is the true value. So how different is the true value? So it is equal to this. So from here I can calculate the, I can take the true value. So this is the true value. And then this I will not change. So then I will put F4, then minus the calculated value divided by the true value. Again, I will not change it, and then times 100. So true percentage error over here is 100. Okay, that is okay. But for the next trials, it is 11.8%. So it is 11.8. So 8%. Okay. For the next trial, it is even much smaller, 0.14%. Okay. And then from then it is even much smaller. Okay. So what we can see over here is that for our general purposes, this much error in the true errors is acceptable. So you can see that the solution is converging very rapidly by this method. Okay. Okay, so you can see that this is the solution, and the solution is converging very rapidly. Okay. Okay. So next is that thus the approach rapidly converges on the true root. So notice that the true percentage relative error at each iteration decreases much faster than it does in the simple fixed point iteration method. So if you compare the results with the previous method, we can see that it's the convergence is much rapid. So in the simple fixed point iteration method, the convergence was linear, but here it is much higher than the linear. Okay, much higher at the convergence is much higher than the linear. So it is a rapid method for convergence to the true solution. However, this method may fail also sometimes. So let's see one example. Okay, so this is the example. So determine the positive root of x to the power 10 minus 1 is equal to using the Newton-Raphson method and initial guess of x is equal to 0.5. So in this equation, if you have this equation x power 10 minus 1, and then that is equal to 0, and then you can say that it is quite obvious that the true solution is x is equal to 1. Okay, but of course we know this true solution is x is equal to 1. But for illustration purpose, if we want to apply this Newton-Raphson method, x is equal to 0 by an initial guess of x is equal to 0.5, can we find that this solution will converge? So this we can see. So by the Newton-Raphson method approach, so we can see apply this formulation. Okay, xi. The function is x to the power minus 1. And you know that for x to the power 10 minus 1, the derivative will be 10x power 9. Okay, and then minus 1, that is 0. So 10x power 9. So if we apply this derivation and then want to determine the solution, so we will see that the solution will not converge very quickly in this case. The solution will not converge very quickly in this case. So let's see in this Excel, so how these values are obtained. Okay, so I is 0, 1, okay, and then maybe say like 20 iterations, okay, and now xi is equal to this. So I start from 0.5 in this case, okay, 0.5, and then now I apply the Newton-Raphson method over here. So it is equal to xi minus f of x. F of x is x power 10 minus 1. Okay, so 0.5 power 10 minus 1 and divided by 9x power 9. Okay, 9 times x power 9. Okay, so I hope I applied it correctly. So from 0.5, I get a completely divergent solution of 0.57. Okay, and in this case, yeah, I get like this, and then I just drag it down and go up to like 21 iterations. So you can see that in this case, it is obvious that the correct solution is 1. Okay, but we are moving towards the correct solution 57, 50, 50, 45. But even after 21st solution, the correct solution is away more than 500%. So maybe it will converge very slowly. Yeah, now it is converging, yeah, to 1, something like this. But the convergence is taking place after, say, something like 200th iteration. So in this case, sometimes the convergence is not that fast in this case. In sometimes, yeah. So here you can see that after 200-second convergence, so this value is about 1.00, or maybe I can take more number of digits. If I show the, yeah, so now the solution has almost converged over here within the solution has converged to something like 40th iteration. Okay, it's not almost exact, but within our number of digits which we are choosing, the solution has converged. So the convergence is normally rapid in this method, but for not for all cases. So in this case, you can see that after the poor prediction, the technique is converging on the true value of x, but at a very slow rate. Okay. So let's see the cases where the Newton-Raphson method exhibits poor convergence. Okay. So in this case, for example, when a function is intersecting the x-axis, but changing its concaveness when when crossing the x-axis. So for example, when crossing this x-axis, this function is concave upward, but after it has crossed the x-axis, this function has concaved downward. This reversal of concaveness is represented by the second derivative of that function. So the second derivative of that function will be equal to 0. But that means from the calculus point of view, if the second derivative of the function at the point of this at or near the solution is closely equal to 0, then you will see that the solution will not converge. So how it will not converge? So for example, if we start from x naught is equal to 0, and then we will take a tangent from this axis, and then we will hit x-axis over here, and then from this x-axis we will move towards the curve again, and then we will take the tangent, and then we will hit over here. So what you can see over here is that by each iteration we are moving away and away from the solution. So in this case, the solution will not converge. Okay, so this means that there are also cases in the Newton-Raphson methods when we cannot get the convergence. Over here, what you can see over is that x naught is here. So here in this case, what we have seen over here is that the solution for this curve is here. Okay, but we have chosen our point x naught is relatively away from that solution, and within at that point is closer to that part of the curve where the slope of the curve is almost becomes 0. Yeah, that means slope of the curve at this point is almost becomes 0. So when we will take the in our initial guess over here, so we will see that, so from x0 we will move to x1 over here, and then from x1 we will move to x2 over here, and then from x2 we will move to x3 over here, and then so on we will move to x4 over here, and then actually we will be converging toward some point over here where there will be no solution, because solution is not here, solution is here. So in this case, the solution will converge to some wrong point over here. So and that means in this case, we can get a wrong solution. So to check whether our solution is correct or not, so we should find the value, of the function by using the calculated value of the x, okay? So because sometimes in most practical cases, which is our also purpose, that we don't know the true solution. So how we can guess that we have got the true solution, or the solution which we have got is the acceptable one? So we will find, we can only find out by inputting that value into the function. If the value of the function gives the value of equal to 0, then that will be the true solution. But in this case, the true solution will not be obtained. Okay. So that can only be checked by inputting the values into the true function. Okay. Next is this case. So in this case, the function is the function has many roots. Okay. So suppose if we want to find the root, for example, if we want to find the root, this one, which is near to our approximated value. So by this approach, for x0, we should find this solution, okay? Because this is the closest one. But what we can see over here is that from x0, we will move towards x1. And from x1, we will move towards x2 over here. So that means we will be further moving away and away from the actual solution. So when the curve of the solution is something like this, then that means it's like a sinusoidal curve or like that. So you may find out that we may be moving away and away from the solution. And in the fourth case, when we have the curve something like this, in this case, actually, you cannot see that this solution has no, this function has no solution at all. No solution at all over here. But in this case, what you can see that we can, from here, we can move to this point, and then from here we can get a horizontal tangent. And when we get a horizontal tangent, this means that the value in the formula of the Newton-Raphson method in the denominator becomes 0. And then when the value in the denominator becomes 0, then that means we cannot further calculate this formula. So this formula will simply fail to provide the solution. So these are the 4 cases in which the Newton-Raphson method can fail. Okay, so I hope the point is clear. So, do we have any question?
No.
No.
Okay, so the next is the secant method. Okay, so this was some discussion about the Newton method. The next is the secant method. So as we have found out that there are some drawbacks in the Newton's method. So in order to rectify these drawbacks, to not exhibit, to not encounter those drawbacks, so there is this secant method. The secant method is very much similar to the one of our previous method, which is called as the false point method, okay, which we discussed in the previous case. But there are some differences between the false point and the secant method. Okay, false point is the bracketing method. Secant method is not the bracketing method. Okay, so the secant method is obtained with the slight variation of the Newton's method for functions whose derivatives are difficult to evaluate. So for these cases, the derivative can be approximated by a backward finite divided difference. Oh, okay. Yeah, so one of the thing in the Newton method was that we need to find the derivative of the function, but for sometimes there are functions for which the derivatives cannot be easily found out. So in those situations, instead of analytically finding the derivative, we numerically estimate the derivative of the function by the backward finite difference method. Backward finite difference methods were briefly discussed, briefly introduced in I think topic 2 or topic 3. Yeah, if I remember, but I skipped that part from those topics because later on we will find out we will study these topics in later in details in this course. So, but as of now, for to apply the secant method, we can say that the finite difference method by using the backward finite differences, we can estimate the derivatives. Okay, and why do we need to estimate the derivative? Because because in the Newton-Raphson's method, sometimes it is difficult to analytically find the derivatives. So then we will numerically find the derivative by the finite difference method in the secant method. But of course, we are not going to find the finite difference method as we will do later on in this course. We will just apply the formulation, and the formulation is something like this. So f prime of that is the formulation is f prime of x is equal to f x I minus 1. That is for the function, the value of the function evaluated for the previous term minus the value of the function evaluated for the current term divided by the previous term minus the current term. So this is the formulation for the backward finite difference method. And then we can see from here is that by simple simple algebraic manipulations, the Newton-Raphson method can be converted into this formulation. Okay, so this is the same as the Newton-Raphson method, but using this formula into the Newton-Raphson method. So in this case, what we get over here is that similarly in the numerator we have the function, the value of the function, but that is multiplied by the difference of the values in x, and then we have the difference in the values of the function. Okay, so in this case, as you can see that we don't have to calculate the derivative of the function in this secant method. So we are simply numerically representing the derivative of the function in terms of the values of the function itself. Okay, so this is the advantage of this method. We don't have to calculate the derivative of the function. So that is the secant method. So it requires two initial estimates of x, for example, x0 and x1. And however, because f of x is not required to change signs between estimates, it is not classified as a bracketing method. If you remember in the false position method, we also need 2 points. But in the false position method, we need 2 points where the value of the function of x need to change the change in sign. But in this case, we don't require that. Okay. So we will first estimate the value of the function at 2 points, and then we will apply this formula, and then by the successive application of this formula, then we will calculate the approximation. So the secant method has the same properties as the Newton's method. So convergence, normally it converges rapidly as the Newton's-Raphson method. However, as the Newton's in the Newton's-Raphson method, it is not guaranteed to have the convergence. So the same is in this case. It is not guaranteed to have the convergence as it was in the Newton's-Raphson method. So the only difference from this method, only advantage for this method over the Newton-Raphson method is that for those cases where we cannot easily find the derivative analytically, then we can find the the root of the equations by this method. So this is how this method is represented graphically. So in the Newton's-Raphson method, we would normally take the tangent to this curve, okay? But in the secant method, we will take the secant. Secant is basically the line which is connecting 2 points on the same curve, okay, which is connecting 2 points on the same curve, whereas tangent is the line which is only connecting 1 point on the curve, okay, only connecting 1 point on the curve. But the secant is the line which is connecting 2 points on the same curve. So in this way, gradually we move towards the solution. So from xi, then we have moved to xi minus 1, and then we have found this point. And then by the successive application, we can move closer to the value. So this is also shown with the help of this example 6.6. But we have almost run out of time. We have run out of time. So therefore, I will stop at this point, and I will continue this topic in my next class on Friday. So that's all for today. So do you have any questions?
No.
No.